All right, so now we're ready to go ahead and work through an example. And this is going to be of the first property, section 4.3.1. And we're looking at this first property right here. L of e to the ATF is equal to f of s minus a. So I'll go ahead and write that we're using L of e to the AT f of t is equal to f of s minus a. And the example is that we're trying to compute the Laplace transform of L of e to the 5t times t cubed. And what we have to remember is that we know, L of t cubed, we could go ahead and find using our Laplace transform table from last week, where we're looking at some n equal to 3 right there, L of t to the n, which would tell us that it's like n factorial over s to the n plus 1. But for us, since n is 3, that's 3 factorial over s to the 3 plus 1. So that's going to be 3 times 2 times 1 over s to the 4th. So that's just 6 over s to the 4th. And that's our capital F of s. And then if we want to compute L of e to the 5t, t cubed, we're going to be using this property where we have some function f times e to the at, but here our a is 5. And we know that the property says that it'll be f of s minus a. So that means that this is going to be 6 over s minus 5 to the 4th power. And that would be our answer. Going a bit more quickly, let's just do one more quick example. If we wanted to do L of e to the minus 2t cosine 4t, we would kind of remember that L of cosine 4t is going to be that kind that has s squared plus k squared on the bottom, like that. And then on top, the cosines are the ones that have s's. The sines are the ones that have k again. And that's our k equals 4. So then L of e to the minus 2t cosine 4t has a equal to minus 2. So that's going to be f of s plus 2, s minus minus 2. And so that's going to give us where we just replace s here in our f of s with s plus 2. So we're going to have s plus 2 over s plus 2 squared plus 4 squared. And there might be some temptation to go ahead and say, okay, that's s plus 2 over s squared plus, 4s plus 4 plus 16. So s squared plus 4s plus 20, like that. And I would say in this section, don't start to simplify things until you have to. Because when you think about doing the inverse Laplace transforms like this, it's helpful for you to be able to see that there's like an s plus 2 in this term, whereas if you multiplied it out, you wouldn't see that anymore. Let's see, we're at 4 minutes. We can go ahead and work with the inverse in the same video. So this is going to be, another example. I cannot do writing example today. 4.3.2. And we're just thinking about the inverse of the property we just talked about. So instead of L of e to the at f of t equals f of s minus a, we're thinking about L inverse of f of s minus a is going to give us e to the at times f of t. And the specific problem for this is that we're trying to compute L inverse of 2s plus 5 over s minus 3 squared. And so kind of thinking about that warning I just gave you, think about how hard it would be to puzzle this out if it was L inverse of 2s plus 5 over s squared minus 6s plus 9. You'd be like, oh, I have to factor this and do a partial fraction thing. I don't know. So what's actually going to help us here is that we want to compute this inverse. And what we're going to do is we're going to say that there's this s minus 3 term. So we think maybe 2s plus 5 over s minus 3 squared is equal to some f of s minus a. And since we see that s minus 3, maybe we think that this is some capital F of s minus 3. And we're just going to try to shape this fraction that we started with so that it looks like things that have terms s minus 3 all over the place. So what we've just said is maybe a equals 3. And if we look at our 2s plus 5 over s minus 3 squared, what I'd like to have is an s minus 3 up top and on bottom. And so I want to make sure to keep this all the same. So I had a 2s before, so I would probably have 2 times that s minus 3 to get my 2s back out of it. But that gives me a minus 6. And since I want this to be 2s plus 5, I need to add enough out here so that it becomes plus 5 in the end. So I add 11. Then if I kind of multiplied this out, I would have 2s minus 6 plus 11 is 2s plus 5. So I did all my algebra right there. Maybe I'll make a little note right there. Actually, that's going to be harder to read. So hopefully you just remember when you're reading these notes that plus 11 came from trying to make a plus 5. And so what this looks like is 2 times s minus 3 over s minus 3 squared plus 11 over s minus 3. Or just 2 over s minus 3 plus 11 over s minus 3. Oops. Forgot about that squared right there. So all I did in these steps was algebra. I said if I have a sum in the top of a fraction, I can break it up into 2 fractions, and then I just canceled out these s minus 3's to have only 1 in the denominator. But now this looks like 2 things that I can take the inverse Laplace transform of. So L inverse of 2s plus 5 over s minus 3 squared would be the same as L inverse of 2 over s minus 3 plus 11 over s minus 3 squared. And that's going to be, by linearity, 2 L inverse of 1 over s minus 3 plus 11 L inverse of 1 over s minus 3 squared. And this is where our new property comes in. So if we note, there's a squared down here. So L inverse of 1 over s squared would just be L inverse of 1 factorial over s to the 1 plus 1. So I know that that's just t. And that would be my little f of t in this example. And that would mean that this right here is capital F of s minus 3 for f of s equal to 1 over s squared. So then what I'm looking at for my problem, 2L inverse of 1 over s minus 3 plus 11 L inverse of 1 over s minus 3 squared, is that the first we can actually just take using our Laplace transform table. The L inverse of 1 over s minus 3 is e to the 3t. And then for the second, we're looking at L inverse of f of s minus 3. So that's going to be e to the at times f of t. So e to the 3t times t. So there's our f of s minus 3. So our a equals 3. I'll go ahead and underline this term. Oh, I don't need the 11. This term created this term. And then this one was, something that you knew how to do last week. And then that's the answer. So what you're going to find with most of these Laplace transform problems is that the inverse is a lot more difficult than the forward direction.